So we are very happy to have Boris Bukh of Carnegie Mellon University, and he's going to talk about empty access parallel boxes. Take it away.
Okay, thank you. Thank you, Isabella, for the invitation. Thanks everybody for joining in. Okay, so the problem I will tell you about is, well, the problem of empty access parallel boxes. Let me tell you what the problem is, and then I will tell you a little bit why anybody would care about it, and also tell you what new we can say about it. Um, okay, so problem is this: um, the setting you have unit cube. So this is my picture of 0, 1 to the d. Okay, so again, picture is planar, but I will definitely think about d going to infinity. And I've got some set of points p inside. And what I want to find axis parallel box which contains no point of p, and that's as large as it can be. So what I want is a large, a large axis parallel box containing no point of p. All right. Again, and I will always use, I will drop the word axis parallel. I mean, all the boxes will be axis parallel in this talk. And I will call this kind of boxes empty boxes, again, to save myself speaking and writing. Okay. So if I have a set P, I can look at quantity M of P, which is the volume of the largest empty box. So it's the maximum volume of a box B, so where it contains no point of P. So B is a box. And again, when I say box, I mean, again, it's got to be contained inside this ambient space, which is the 0, 1 to the D. Again, I'm not allowed to take something which is just all over there. Okay, I'm not going to repeat this, but this is implicit. Okay, so this is box. Okay, let me just write it once, and I will not write it again in 0, 1 to the D. Okay, and we want to, on one hand, we want to say, well, no matter what set P you give me, I'm going to find a very large box. That's one thing I want to say. On the other hand, I want to say, well, there's actually some sets where there isn't a particularly large box, empty box inside. Okay, so in other words, what I'm interested in is a quantity which I will denote md of n. So that's the best value of m over all n element sets P. Okay, so in other words, this is the minimum over all n element sets P of m of P. And again, P is inside 0, 1. Okay. Just to make sure we understand what this quantity is, let me just show you a very simple, I would say, obvious statement about it. So, okay, so now the trivial thing is that m of d of n is at least 1 over n plus 1. Okay, so if you decode what the symbols mean, that means that no matter which endpoints you choose inside the unit box, I will be able to find an empty box containing none of the points you chose of volume this big. Okay, so let's see how it works. Okay, so this is the box. You chose some points inside. And so what I'm going to do, I'm going to project them down onto the first coordinate. So this is my projection. So what I'm going to get, I'm going to bunch of points on the union interval. And I'm going to look at what's bunch? It's n. Oh, because my points p has n points. So there are n plus 1 intervals that they cut the unit interval into. And I'm going to take the largest interval. Okay, well, I think in this picture it's going to be this one. Okay, so in this case it's going to be this biggest interval. And I'm going to take a inverse image of that and the projection. So in other words, it's this box. Okay, so this is my box and it's empty. Again, well, it contains 2 points on the boundary, but I can shrink it tiny, tiny, tiny bit without changing volume to speak of. Okay. So that's an argument for a lower bound. Hopefully will make this jumble of symbols clear. So what we want to know what this thing is, how it behaves. Okay. This quantity m is called in the literature dispersion. It's just a name. And the reason why we care about this is because it's besides looking at it looks like a pretty problem, is because it's related to some problem which is more important, and also it's important a little bit, not too much, on its own right. So what is it related to? So there is a related notion called discrepancy. So if you were in pre-talk, you know what that is. If you don't, that's okay. So if dispersion measures basically how if it measures how big of an empty box we can have, so it measures big empty boxes. Discrepancy, you can think of it measures boxes with too few or too many points. So, because an empty box it's a box with too few points, right? If they find a huge box which is empty, well, it's kind of strange because we have a big set and here it is, we have a large box which is empty. Shouldn't happen, right? It's too few. But and similar thing it might happen again. Well, maybe find box with too many points, or maybe too few, but not literally zero. Okay, all kinds of things may happen. So this discrepancy measures that deviation from expectation. Okay, I won't write a definition of discrepancy in this talk. So it's a related notion. It's slightly more sophisticated notion than dispersion because it measures something more refined, but they're related. And each of those problems comes from partly from an application. So discrepancy, as I mentioned in the pre-talk, arises in the problem of numerical integration. So you've got a function on some domain, highly measurable domain, say it's a cube, and you want to approximate its integral by computing at some points and aggregating those measurements. So what you need to do is you need to select a set of points which have a low discrepancy, evaluate function at those points, and then average that. That tends to be the correct thing to do. Now, dispersion is a cruder quantity, so it doesn't allow you to integrate functions. Okay, so again, this would be nice, but it doesn't. But it allows you to solve some, maybe less exciting problem of approximating rank 1 tensors. Again, I don't expect people to have heard of this problem or care about this problem. So I will not try to describe what the problem is. Roughly, it's some kind of class of functions, high-dimensional functions. And you again try to reconstruct what this function is from some samples. And again, so the right thing to do is, again, you evaluate it in the low dispersion set. Okay, so there's two similar problems, each with its applications. Okay, this is why we care. And also it's pretty. I think it's pretty, but you might disagree. All right. So hopefully that's enough of a motivation. Let me tell you what we know about this, and what new can we say about it. All right. Okay. So this is trivial. What I'm going to focus on this talk is the behavior of the dispersion as number of points gets bigger. Okay, so in other words, what I'm interested in this talk, I mean, it's not the only thing you could look at, but this is what I'll focus now at, how it behaves as n gets bigger. Well, it's got to grow at least like 1 over n. And it turns out, okay, and hopefully I'll be able to explain a little bit about that it does grow just like 1 over n. So what I'm going to do, I'm going to multiply it by n, and I'm going to look at the limit of this again. As n goes to infinity. So, and I will denote this limit by c sub d. Okay, it's easy to see that the limit exists. Okay, so let me just sketch an idea of the argument so that people at least believe this. So the idea is this: you have, again, your unit box, and you have your point set. And then what you're going to do, you're going to cut it in half, say. I mean, this is an idea. You're going to cut 2 points here and n over 2 points here. So basically, this is, so on the left you have a box. Okay, it's not a box whose sides are equal dimension, but you can scale one of the dimensions to it's actually really a box. So I'll still call it a box. Okay? It's a box on the left. It's a box on the right, and it has n over 2 points on the left and n over 2 points on the right. So you can basically now use what you know about sets with n of size n over 2. Okay, so you manage to relate the value of this function at n and n over 2. Okay, and if you write that relation, you will instantly see that that it says that this quantity here is monotone when you restrict it to powers of 2, for example, because you relate n over 2 to n again, so 2 to 4, 4 to 8, etc. It's monotone, therefore the limit exists. The monotone sequence converges. And if you do the same argument instead of partitioning in half and half, but in some other ratio, you can show, in fact, that it converges not only along powers of 2, but it really converges. Okay, so this is some kind of argument, which is, I probably made it sound more complicated than it is, because I wanted to give an idea, but it's okay. It's not difficult. Again, okay, limit exists. Okay, and by what I've written over there, the limit, this constant is at least 1. Okay, so what was known prior to work I'm going to tell you about? Okay, so there was a work of Zhang and Dumitrescu, which show that this constant is at least 5/4 for a dimension at least 2. There was a work. Okay, for this I will need to take a piece of paper because I will certainly make a spelling mistake otherwise. Eisleitner, Hindrich, Rudolph, sorry, Rudolph. And so this was actually somewhat more exciting bound because it showed actually it goes to infinity um, like a log, at least like a log. Okay, and um, what about the upper bounds? In other words, constructions. Can we make a set where it's not too large? The best construction was to go to larger, showing that C of D is at most the and something exponential in D. Yeah, 128 to the D approximately. So what I want to tell you about today, this is this joint work with, oh, I erased, unfortunately, okay, let me just write it again. Ting-Wei Chao. I joined with Ting-Wei Chao, who's a graduate student here at CMU. So we can improve some of these bounds, both lower and upper bound. So on the lower bound is 2D over E. Again, E is the base of natural logs, 2.7, etc. And the upper bound is, okay, there's some constant here. I think in our paper it's 8,000, but you shouldn't take numbers like 8,000 too seriously. Again, as in, it's true with 8,000. It's certainly true for with 4,000. We didn't try to optimize. Okay. So the main thing is this bound is polynomial, neither logarithmic nor exponential like previous bounds. So we don't. I mean, we haven't settled the problem, unfortunately. Again, it's most of the times, at least when I try to solve a problem, I don't solve it. Well, okay, that's life. So what I want to do, I want to tell you idea behind the lower bound, and maybe a few words about upper bound, but I will definitely not be able to tell you proof of upper bound. It's more complicated than the lower bound, so that alone would take more than a single lecture. And so I will try to say a few words about upper bound, but again, we'll have to cut it. Okay, before I start going with the proofs and et cetera, I want to pause and see if people have questions, concerns, or anything. Yeah. Okay, well, people seem to be okay. Somewhat happy. Okay. So let me then continue. All right. So what's the how does the lower bound look like? So I will not prove you the lower bound which I wrote here. What I will prove to you is a weaker bound that C of D is bigger than some multiple of D over log D. So it's this says it's linear, at least linear. This says it's at least D over log D. So I will give you a simpler proof which loses the logarithm. Okay. All right. And the idea of the proof is similar to the idea what I showed in the press seminar for those of you who were in press seminar. But so in the press seminar, I talked about discrepancy of convex sets, and there is a mantra in a high-dimensional convex geometry that that say any kind of high-dimensional set kind of looks the same. They look right. I mean, usually if you look at pictures, it looks some kind of spiky. You always see this kind of spiky pictures. They always look the same. So in particular, the boxes, which we're interested in, I mean, they don't that different from convex sets. Okay, so anyways, enough of philosophy. Let's see the proof. So I will take um, a standard box of volume constant over n. So C is a box of volume R over n. Okay, so I'll draw a picture. And again, I have not told you what the number R is. I will choose it shortly. So it's a mystery for now. So picture is this. Again, this is my box C, and I will choose it so that it's centered around the origin. So its coordinates are from negative delta to plus delta in every direction. Okay. So C is from negative delta to delta to the D. And again, and I choose delta, so its volume is this. Okay, you can compute what the delta is. I'm not going to do it. It's not going to, we don't need it. We need the volume. We don't need the value of that. Okay. And then I'm going to look at the random shift of this box. So I'm going to take I'm going to take a random x, and I'm going to shift it by random x. Okay, and when I'm choosing x at random, well, I want to cover. So okay, this is my picture is not to scale because we should think of the delta as very small and much smaller than constant one. But again, I cannot draw it realistically on the board. So this is my this, and this is 0, my 0, 1, which I drew only slightly bigger. And so what I'm doing, I'm taking this and I'm just moving it around this unit box. And I want to cover every point equally often. So for that, I'm going to take x to between negative delta to plus 1 plus delta to the D. So I'm taking random x uniformly from this set. And I'm looking at translate of C. So okay, so it's basically, okay, so this is my C plus x. Somewhere inside my 0. Okay. Now, if I have some point in my set P, what's the likelihood that is going to end up in this random translated box? Well, it's going to be the same no matter which point P I'm going to pick. Because, right? It's because it's okay. So okay, if P, then what I'm writing probability that P is inside this box, it's going to be the same for all of them. Okay, if you want, it's just probability that X is going to be. Oh, by the way, I apologize for not warning people. The camera shuts off every half an hour automatically to prevent overheating. I just turned it back on. You should be able to see picture again. Okay, wait. Hello, can you see the picture?
Yes, we can.
Good. Okay. Okay, something is going strange. On my screen, it looks like there's some kind of lag. Let me try to restart this thing. Yeah. 1 second. Sorry. That usually helps. I'm sorry. Give me a second. That's boom. Okay, that should be better now. Okay, very good. I see I see people nodding. I can see you, so do feel free to nod. Okay. All right, so let's continue. So it's this probability is the same thing. Probability that x ends up in the properly translated copy of C. Okay, point is it's the same number, and therefore its probability is going to be in this box. It's literally really essentially the volume of this box with some small fudge factor, because again it's not totally uniform around the boundary. Again, so it's not, again, this is not 0 to 1. You need to divide by volume of this. But okay, whatever. So this is equal to the volume of C divided by what this thing is. What was delta to the power D. Okay, which is okay. I'll just basically say it's basically the volume of C. And again, okay, again, people work. Okay, so this is basically R over N. Okay, so probability you capture a given point is proportional to the volume of the set. Nothing surprising. All right. So let's now consider inside C a smaller sub-box. Okay, so I will denote it C0. So this is inside C. And what is the C0? C0 is a sub-box whose volume is 1/2. 1/2 of over N. Now, probability that with same logic, the probability that at some point, a given point P happens to be in the translate of C0. So as I translate C, it also translates C0. Well, it's going to be basically 1 over 2N. So the expected number of points which falls inside this translated box, well, if each of them has probability of 1 over 2N being inside the box, well, what's the probability that, what's the expected number of them which do fall inside the box? Okay. Anybody?
Well, n times that probability of
Yeah, exactly.
So
this is
1/2.
A half. Correct. It's a half. Or I mean, or okay, so okay. Or probability, particular probability this thing is empty. Probability none of them fall there. Well, it's going to be at least a half. Okay, so this can there's several ways we can say the same thing. Well, M was the same. All right. So this the smaller box is inside C. It's M is always empty. Well, half the time it's empty. Good. And we also know that the expected number of points which fall inside C by the same calculation, which is the same calculation we just done, but instead of C0, it's a C. The only thing changes, instead of a 1 over 2N, it's R over N. And I haven't told you the value of R, but we still can do the calculation. So the expected number of points falling there, it's basically R. It's basically R, because it's R over N times R. Okay. In particular, the probability we're going to get far more points than expected. The probability we expect R points. Probability we're going to get more than 2 R points. Well, it's no more than a half, because if it were bigger than a half, this expectation would be too big. It would be something bigger than a half times 2R, that's too big. So this probability is no bigger than a half. It's small, okay, smaller than a half. Okay, so in particular, well, we have two events. This event, the probability of this event, probability is non-empty, it's most a half. Probability is bigger than 2R, is at most a half. So the positive probability, both of these events hold. So that means, in other words, there exists some C. There is some translate such that both this translate is empty and there are not too many points elsewhere. P of C is less than 2. Okay. So we're going to pick such an X and fix it. And then we're going to look at this translated box and we're going to modify it so to make it empty and still large volume. Again, for people who were in press seminar, it should remind you of what we were doing with the disk and the flaps. It's going to be a similar idea. Okay. Okay, so what are we doing? So first of all, I'm interested in finding an empty subbox inside C plus X. Empty meaning not containing any point of P, but I can translate the whole picture. So instead of translating C, I can translate P. So what I'm thinking instead, I'm looking at my P minus X, and I want to look inside C. It's equivalent, it's just shifting my point of view. And it's going to be slightly more convenient for drawing pictures and thinking. Okay, so again, so let's, again, I already have conveniently here a picture of C and C0. And my X is chosen so that there are no points here. This is already empty. That's good. We like empty boxes, but it's not big enough. It has only volume 1/2 times 1/n. It's really, really small. And we also know that there are very few points, well, very few meaning no more than this number, which we haven't chosen yet, but we think of it as very few. There are very few points elsewhere. Well, so what about those other points which are there? Every other point has at least, since it's not in the center box, at least one of its coordinates is large. So for every point inside P minus X, there exists a coordinate I such that the PI is large. It's bigger than, okay, let's give me a name to this. We call this as epsilon. Minus epsilon. So this is inner box has dimensions from negative epsilon to epsilon. So if it's bigger than epsilon. Okay, so there's some coordinate in which it sticks out. Okay, so let's for each point we're going to assign such a coordinate. Sorry. And then what? Then let me draw a picture. So say I'm drawing to, okay, since I'm in 2 dimensions, I cannot draw too many points. It's a low dimension, only 2. So I'm going to draw 1 point. And I'm going to explain what happens in that case. So say this is the point which happens to fall inside my C. And then I want to find an empty box. So what I'm going to do, I'm going to cut it off. So what I'm going to do, I'm going to draw things like this, and I'm just going to remove this flap of my box. So this part is an empty box. Okay. Okay. Now, just to make it a calculation which I'm going to write tiny bit easier, what I'm going to do, I'm going to remove not only this flap, but also the one which is symmetrically opposite. Again, this is not necessary, and you do get better bound if you don't do that. But the calculation is becoming a tiny bit more complicated, and this is a seminar, so I don't want to do more complicated calculations. So what I will remain with is this set. This is going to be my empty box. And of course, there might happen there is more than one dimension which I need to cut off. So, okay, fine, I remove several of them. So what will happen is that there are some coordinate directions which aren't changed. So there are, I'll obtain in those coordinate directions, I will get my box will go from negative delta plus delta, so negative delta plus delta, and there are some other directions which I did cut off, will go from negative epsilon to plus epsilon. So my volume will be product of those epsilons and deltas. Okay, so let me write it. So I cut the flaps, and I get an empty box C prime. And what's its volume? Well, it's not difficult. So volume of this is going to be basically the volume of the box I started with, C. Except each time I cut the flap, I'm replacing the delta by epsilon. Now, if I replace none of them, I will just get this volume of C. If I replaced all of them by epsilon, I will get a volume of C0, right? So I'm interpolating between the volume of C and the volume of C0, and if I do 0 steps, it's the volume of C. If I do these steps, I'm going to get volume of C0, and it's geometric, so I can write down the formula. So it's volume of C times I'm going to lose the volume of C times volume of C0 times the number of steps I do. So, okay, let me write so let's say this size of this set, I don't know, let's call it C. So this is number of sets which happen to fall inside this box. So I do it T times, and again, I just need to scale by D. So if I do it 0 times, I get volume of C. I go do it D times, I'm going to volume of C0. This is the formula, literally the formula. Okay, so now, and I know a bound on T. T is not large. T is at most 2R. And I need to choose R, but I can choose it small. So let's do it. I don't need a picture anymore. So it goes. All right. So okay. So we know volume of C. It's R over N. We know volume of C0. It's a half. We also know it's about half over N. So this ratio is basically R. So this is about 2R. 1 over 2R. I put a negative sign because I flipped. T is at most 2R. So 2R over D. That's it. That's, again, I might have, actually not approximately, sorry. This is at least, because again, I'm using an upper bound on T. T might be smaller, so it's not approximately. Okay, so now I need to choose. So now I'm done. Why? Because I get the lower bound for every value of r I want to choose. So now it's a calculus problem. I just need to choose a value of r which will make this number as large as possible. Okay, well, I'm not going to calculus in front of you. I will embarrass myself. So I will go. But if you do it, you're going to get the optimal choice of r is approximately d over log d with some constant which I'm not going to worry about, but d over log d works. And if you plug it in, you're going to get d over log d, 1 over n, this is this term, times, again, d over log d. I'll drop the constant, 1 over log d. Again, there's some constant here. And again, moving d to exponent, okay, so d, it's d the same thing as e to the log d. This is basically a constant. So this is basically a constant. Okay, so we are left with d over log d times 1 over n. Okay. So this gives you a lower bound of d over log d. All right. At this point, again, I want to pause. Actually, I think my time is essentially up. So maybe I will probably even.
You still have 9 minutes.
9 minutes? I thought I was supposed to be.
It goes until 5 because you started at 4:10, and then we have 10 minutes for questions.
Okay. Well, okay. Still, I want to pause because again, rather than for me saying more things and losing everybody, again, I have questions about this proof or anything. All right. Well, most people are looking at their screens, which presumably means looking at the board. So, okay, let me continue. Okay. So this is a lower bound. The upper bound. So I will not even try to tell you how to get the polynomial upper bound, but I will tell you the idea behind how to get any upper bound, I'll show this C of D is actually finite constant. So your limit exists, it's easy. But why is it finite? Like you need some construction where largest empty box has size constant over n. Okay, and this is far from obvious. I mean, the most obvious thing you're going to try to do, I mean, I would try to do if I never seen this problem, take say a random set of points. This fails. It would be like log n over n rather than constant over n. It's very not obvious, even in dimension 2, how to do it. So I will tell you how to get some upper bound, and maybe I'll say one word about the difficulty one has to overcome to get a good upper bound. Okay. So here is a construction of a set with a small dispersion. I'm going to define an operation on integers, which is rather strange looking. It takes a number and reverses its digits. So let me write it. So if I have a number m, and I'm going to write in some base, which is going to be prime, always prime. So it's going to be, say, a sub t minus 1, a0 in base p. Okay. Then its reversal, base p reversal of m, is the number whose base p expansion is obtained by reversing the digits. So basically, I start with a 0, then I put a decimal PRA point, and then I'm going to write the digits in reverse. Okay. Yeah, I know. This is again, if you know about rings and this is not something you do to element of a ring, reversing digits, right? Okay. But anyways, this is the operation. So here is the set P. So this is an element of 0, 1. This should be clear. So let's take a set P that is whose x coordinate is the base 2 reversal of a number m, and y coordinate is the base 3 reversal of a number. Again, there's nothing too special about 2 and 3. Only thing I really care is it's 2 different primes. And m is going to arrange over suitable set. In this case, suitable set is the some long interval. Okay, so let's say it's an interval from 1 to n. Okay, here it is. So this is a set. It has endpoints because again, it's just image of interval of length n under some very stranger looking map. And I claim that its dispersion is bounded by some constant over n. Okay, so let's just see it. So the important thing about such a construction. Okay, so in x coordinates we care about the binary expansion of a number. For the y coordinates we care about a ternary expansion of a number. So we are going to look at the intervals which are dyadic in the x coordinate. So a over 2, say b, a2 to the b. Okay, so let's just make them like this, and which are ternary in the y coordinate. So c over 2d. Oh, d is a bad letter. E. And c plus 1 over 2e. Okay, so we look at intervals like this. So let's call them elementary intervals. And I'm claiming that if I take a look at any elementary interval, then if it has a large area, again we're in a plane, so it's area, then it contains a point of p. So in other words, there are if you were to define dispersion only with respect to this special intervals, then dispersion would be small. Well, okay, I'll prove by example. I don't want to write a full proof. It's a proof by example. So this is my unit square. Again, I'm interested in dyadic in x coordinate. So this is my 1/2, and ternary in the y coordinate. So this is like this. So I'm going to now take some box of this shape. So this is a box from an x coordinate from 1/2 to 1, and from 0 to 1/3. Now, so let's call it box B. So what are the points which are in the intersection of B in P? Well, they are in correspondence with those numbers m, which, well, in binary, if I look at the first digit in a binary expansion of, it's a 1. So what's the first digit? It's a 0. So that means the least significant digit of m in binary is 1. So, or in other words, it's m modulo 2 is 1. Okay, similarly, if I'm interested, now what's the condition that it happens, it falls into this interval in y coordinate direction? Well, it's not so difficult. Again, it means the first digit in ternary after the decimal point is 0, which again means that m is congruent to 0 mod 3. Okay, but of course by Chinese remainder theorem, that's the same thing, that m is congruent to what is it? Wow, I should have 3 mod 6. Okay, that's the Chinese remainder theorem. So Good. And more generally, if I take some box, I mean, the saying that it's in of elementary box, I will get a condition mod 2, condition mod power of 2, another condition mod to the power of 3. So this will be the m will be congruent to something. So saying that m is our infinite progression. And if I take progression whose step is smaller than n, it will contain a point of this interval. So that's that simple. And the step of progression is exactly one of the volume of this box. So this shows you that every elementary box of not too small volume will contain a point of the set. And okay, and if you're interested in the non-elementary boxes, well, what you do, you're going to take a box which is not elementary, and you're going to find as large an elementary box inside as you can. Okay. Now, if you do it, you might have to shrink the x coordinate by a factor of 2, and you might have to shrink the y coordinate by a factor of 3. So you will lose a factor of 6. Okay. And in general, if you do a similar argument in dimension D by enrolling more primes than 2 and 3, you might lose a product of those primes. So you're going to get a loss which looks like, well, d factorial or something. The product of d numbers like d factorial. And a larger, kind of smarter idea. Okay, not partly him and partly whom he built on, which is a whole huge line of works. Of most important singular de Ruyter's work. We're not telling you anything about those, which allows you to replace the d factorial by exponential in d. And what we do is circumvent this problem of shrinking in a different way. We replace this interval, which is used in all previous works, by a different set. And then essentially union of some two carefully chosen intervals, which allows us to lose much less by shrinking. Okay, this is as much as you probe I'm going to say about our argument, because I mean, my time is up. I think I'm 2 minutes over. I'm much sorry. So thank you for attention, and it was nice to see everybody.
Let's unmute ourselves and thank Boris for a wonderful talk. Any questions?
I was wondering about, so when we want to like maximize the dispersion by choosing a set of points, is it true that we could choose the points to be on a lattice? Or has that been studied if we restrict to points lying on a lattice?
Okay. So the best known two-dimensional construction is basically a lattice. Okay, with a small twist, but it's basically a lattice. Okay. In higher dimensions, as far as I know, there is no known good lattice constructions. Again, I don't know a negative result. It doesn't mean it is not in the literature. It just means I'm not aware of a negative result.
Oh, okay.
But again, so all the good higher dimensional constructions, they do employ some version of this digit reversal idea. Again, possibly suitably generalized. I mean, for example, it's like the best constructions are generalized to local fields. Okay, not to work in integers, but same idea. Lattices, I don't know any good constructions in lattices.
Okay.
I mean, there are some. Actually, again, camera went out again because it's every half an hour. Let me just turn it on again. Okay, good. Yeah. Okay, I'm back. Yeah, so that's my knowledge about it.
Yeah, thanks. Yeah.
Any more questions? So what do you actually think? What can be, what is that CD? Which bound is it closer to?
My guess, not extremely firm, but a guess nonetheless, it should be d log d. The reason, again, I don't have a very strong reason. So one is that the lower bound, we are using averaging argument, and whereas there should be some kind of more refined probabilistic argument, like, if you're familiar with something with local lemma, there should be some kind of analog of that, those kind of arguments, which might gain a log on one hand. On the other hand, in our upper bound construction, it's a two-step construction. We construct something which works very well with respect to some elementary boxes, and it behaves kind of d log d kind of thing. And then we lose another factor of d by doing something ugly. Okay, I have no other better word to describe it, to make it work for all the boxes, and losing another factor of d. And again, I don't believe that ugliness has any place in the final picture. So I believe that's why I suspect it's d log d, but it's not a very strong suspicion.
Thank you. Any more questions? And let's thank Boris again.